Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we'll continue with our discussion on logistic regression. We'll talk about connections, and then we'll branch off into SVMs, and we'll talk about SVMs today. So let's start with our basic usual thing. You're given data, so you're given x1, y1 up to xm, yn. So you're given some labeled data. And what you are going to do is, let's say you are going to model P of y condition on x and theta. You are going to write this as being proportional to P of theta, product of P of yi, condition on xi and theta. So you are just going to make this standard IID assumption, and this is how things look like. Right? So you have this part we have seen multiple times in the past, so this is nothing should be surprising to you. So we can now take a negative log likelihood, which is what we are interested in, because we already know that this is, if you work with exponential families, then this quantity is going to be convex, right? So this can be written as minus log of P of theta minus summation going from 1 to m of the log of P of yi condition on x and theta. Right? So this part we have seen multiple times. There's nothing new happening still. And what we are going to do in particular is we are going to assume this to be an isotropic Gaussian. Right? So what that means is that if you take the minus log of P of theta, then you'll just get 1/2 norm square. Right? So this is going to be the log of P of theta. Okay, so this is just an arbitrary choice, and you can choose other priors, and if you choose other priors, you can get other instances, other kind of regularizers. Right? So we discussed this a little bit before. So if you use a Laplace prior, then you'll get a L1 regularizer. If you use a Gaussian prior, you'll get an L2 regularizer, and you can in general use an LP regularizer, or you can also use a conjugate prior. Okay, so but we are not looking at conjugate priors. We are just going to stick with isotropic Gaussian. Okay, this is just a choice. And then for this P of yi condition on x and theta, I am going to choose a conditional exponential family. Okay, so again this you have seen before. P of y condition on x and theta, I am going to write this as x of phi of xy times theta minus g of theta condition on x, and where g of theta condition on x is the log of the sum over y of x of phi of xy times theta. Okay, so this is all familiar, makes sense. Okay, so if I use this as my for P of yi condition on xi, then this can be written as plus summation of g of theta condition on xi minus phi of xi yi times theta, and again I going from 1 to m. Okay, and this is my objective function. So let me just call this g of theta. Okay, so far nothing is new. I haven't done anything that we have not done before. Okay, so up to this point it's exactly the same as what we have done before. And then what we are going to do is, because this is a negative log likelihood, we are going to minimize this, right? And some of the things that Prateek talked about last time, some of these methods can be used. So for instance, if you know how to compute the gradient, and if you know how to compute the Hessian, if you knew just the gradient, you could use gradient descent or some related method. If you are using the Hessian, then we can talk about using Newton method and so on. Okay, but if there's more interest, we'll come back and talk more about optimization. But for now, let me work on interpreting this and showing you some neat things about this. Okay, so any questions about this development so far? Anybody have doubts? Okay, So now let's first do the simplest possible development that we can do out of here, which is let us specialize by assuming that the yi's are going to come from +1 -1. Okay, so this is our specialization for binary logistic regression. Okay, and I want to show you how the specialization works, and also how this is related to the logistic laws, and also I also want to show you. I promised you that I'll show you how it is related to naive Bayes. Okay, so how naive Bayes and logistic regression are very closely related. They're not very different from each other, although some people would like you to believe they are. Okay, so let us start with this. Right? So let's start with the simple assumption that the yi belongs to +1 -1. So if this is the case, what happens to our log partition function? So let us look at this guy first. Okay, so how does the log partition function look like? The log partition function in this case looks like g of theta condition on x looks like log of x of phi of x and +1 times theta, okay, plus x of phi of x -1 times theta. Okay, so this is just from the definition. This is the log of the sum of x puff over all possible values of y. Now I have restricted y to be just +1 -1, so I just substitute it in here and I get this quantity. Okay, so this is what happens. And therefore, what can I do? If I look at this, if I ask what is the p of y equals +1 condition on x and theta, if I look for this, how does it look like? This looks like x puff phi of x +1 times theta, okay, divided by x puff phi of x +1 times theta plus x puff phi of x -1 times theta. Clear? Because there are only two possible cases, right? Y can be either +1 or -1. So my normalizer is the log sum x. If I have the x of the log, those two cancel, and I'm just left with x and x. So I get x plus x. Okay, and clearly you can see this is a density, right? Because it sums to 1. Okay, so in an analogous way, you can write, if you substitute +1 for -1, you can write the same thing. Okay, this I'm going to rewrite in a slightly different way. So I'm just going to divide numerator and denominator by this quantity. Okay, if I divide numerator and denominator by this quantity, this becomes 1 over 1 plus, and what happens here? This is x of phi of x -1 minus phi of x +1 times theta. Okay, do you see that? If I just divide the top and bottom by the same phi of x times phi of x +1, okay, then this is what happens. Okay, and now I'm going to just rename this quantity, because see, this is just phi of x -1 minus phi of x +1, so it's always it only depends on x, right? So if you tell me x, you have told me everything about it. So I'm just going to rename this as phi hat of x. Okay, so now what happens? This is nothing but 1 over 1 plus x of phi hat of x times theta. Okay, and what is this function? This is the logistic function, right? This is exactly the loss. This is, you remember when Pradeep introduced you logistic regression, probably he went this route, right? So he showed you that, or let us assume that p of y condition on x and theta looks like this. Right? We didn't do that assumption. We said let's start with a proper exponential family treatment. Okay, and then from an exponential family treatment, let us make this restricted to +1 -1. Then this is how it looks like. Okay, and actually, in fact, you can verify for yourself. This is not easy to. This is not hard to do. You can verify that p of y equals -1 condition on x and theta can be written as 1 over 1 plus x of minus phi hat of x times theta. And this is not very hard to do. You just have -1 here, divide by -1. You'll get exactly the same thing. It's not very hard. So I can combine the two and basically write the two as follows, right? So I can say P of y condition on x and theta is nothing but 1 over 1 plus x of y times phi hat of x times theta. Okay, and this is probably from where when Pradeep started, he probably started from here, right? Saying let us assume that there is a logistic function, there is a logistic transfer function, right? So we have an x, you take some feature, you multiply it with theta, multiply it with y, and this you apply the logistic transfer function, and that will give you the output that is between 0 and 1. Okay, so this is like applying a sigmoid transfer function on top of a dot product. Okay, but here we didn't have to do any of that. We started from the exponential families and we directly derived this quantity for us. Okay, now why is this interesting? So let's now try to play around a little bit more with this and try to understand more about why this kind of interpretation is somewhat more powerful than just applying the logistic transform. Okay, so first let me show you what happens to the let's first try to understand what happens to the prediction. How do you predict in such a setting, right? Once you have a proper probabilistic interpretation, the advantage is that you can go ahead and actually make these ask these natural questions and answer them quite well, right? Which is, you can say, how am I going to predict? So you remember in this setting, we said whenever we find a theta, after we find a theta, the prediction is simply going to be argmax of P of y condition on x and theta, right? So if you give me an x, what I'm going to do is I'm going to say how likely is each of these labels. Among these labels set, I'm going to pick the one which is the most likely and predict with that, right? So if I have a multi-class class, if I have a lot of classes to choose from, I'll find out what is the probability, conditional probability of each of these classes, and then I'll choose the one which has the most probability. Okay. In this case, for our case, we only have two classes, right? So it is either +1 or -1. So you can say, therefore you can say we will predict P of y if P of y equals +1, condition on x and theta is bigger than P of y equals -1, condition on x and theta, then you predict +1, otherwise you predict -1. Okay? So because we only have two classes, you only have to consider two probabilities. Okay, so you just have to say it's basically like a similar to a Bernoulli distribution, right? Because you just have two possibilities. Or equivalently, I can write this as this, right? Okay, nothing has changed. Or even I can do the following thing. I can take the log on both sides and do this. Okay. Now, what is the log of P of y equals +1 over P of y equals -1? We know P of y has this form. If you use this here, what happens? The P of y equals +1 over P of y equals -1, you just have to do the math. It will just turn out to be phi hat of x times theta. This is not very hard to see, because if you think about it, you have phi of xi yi times theta minus g of theta, but g of theta is common in both, so g of theta cancels out, and then you're just left with phi of x I yi times theta over phi of x I yi times theta. So the both within the exponential, and then you take the log, so you get this. You can verify this. This is again just algebraic manipulation. So what is our prediction rule? Therefore our prediction rule is, if this quantity, if phi hat of x times theta is bigger than 0, then predict +1, otherwise predict -1. Okay, this is our rule. Now I want to show you how this prediction rule, or how in general this prediction that we do in logistic regression is related to what we are doing in naive Bayes. Okay. So far everybody happy? Any questions about any of this manipulation? Okay. So now let us see what we were doing in naive Bayes. Do you remember? If you remember what we did in naive Bayes, we said suppose you are given some words or features, right? It doesn't matter. What we are going to do is we are going to compute the difference in the conditional probabilities of those features. Like for instance, we were computing log of P of Wi condition on y equals spam minus log of P of Wi condition on y equals ham. Do you remember we were doing these kind of transformations? So what we said is we're going to look at each word. We'll say how likely is this word to occur when the email is a spam versus how likely is it to occur when the email is a ham. And if some words have this capability to distinguish a lot more, right, just because they occur more frequently in spam versus ham, like for instance Viagra may occur more frequently in spam than in ham, while on the other hand common words like the, this, the, that and so on may not occur with large difference in frequencies. Okay, and then we just simply did this, and when we had to predict on a new word, we just computed this over all possible words in the document, right? So we just summed this up. Okay, when you do the summation, so now let me call this phi hat of the data x the ith feature. Okay, and I'm doing this deliberately. Okay, so I'm saying that I'm going to think about this as one long vector. Okay, so for every word in your document, what you're going to do is you're going to compute this quantity, right? And then you're going to take the difference and put it in here. Okay, this gives you a vector. I'm going to call this vector phi hat of x. So this is nothing but the ith component of this vector, right? Because this is the ith word, you're taking the ith component of this vector. Clear? And then what you're doing is to predict, you just computed this quantity, and you said if this score was above a certain threshold, you'll predict this as spam, if not, you'll predict this as ham. So in dot product terms, this is what you're doing. You're computing phi hat of x times the vector of all ones. That's what a summation means. Okay, and then you say if this is larger than some constant, I'm going to predict +1, otherwise I'm going to predict -1. Okay, contrast this with what is happening here. There are few key differences. Okay, so first of all, in principle they are exactly the same, but there is one key difference. In logistic regression, these weights theta are learnt. Okay, in naive Bayes, these weights are fixed. Okay, the second thing is that in logistic regression, you have a choice to design the phi hat. Right? You can design the phi hat in whatever way you want. You can say I'm going to look at, remember what was our phi hat, was just phi of xi xy. So this was, if you remember our definition of phi hat, right, was phi of x y equals +1 minus phi of x y equals -1. Right? This was our phi hat. The same thing is happening here too. See, this is a feature of when y equals spam. This is a feature of when y equals ham. And you're taking the difference of the two and you're calling it phi hat. You can do the same thing here. This is some feature of spam. This is some feature of ham. And you're taking the difference and you're calling it phi hat. But here you are not restricted to using the log probabilities of the words. You can use any feature you want. In fact, you can use these log probabilities directly if you want. If you want, you can use some other feature. Okay, so in terms of feature modeling, this is more flexible. But even more flexibility comes from the fact that after you have defined your features, you learn the weights for the features. So what are these theta? You think of this as the importance of each feature. Suppose if theta is 10 for a given feature and is say 2 for some other feature, then what this means is that what you have learned is that one feature, the first feature, is 5 times more important than the second one. In a naive Bayes setting, you don't have that flexibility. You are simply saying whatever it is, every feature, it's like everybody gets an equal vote. Okay, every word gets an equal vote. So you want to determine whether an email is spam or ham, every single word in that email will get a vote. Okay, and the vote is equal. So it's a very democratic process. Here, every single feature gets a vote, but the vote is not equal. Some may be more important, which kind of makes sense, right? So there may be some words which are much more discriminative than the others. And you want to be able to upweight them. You want to be able to give them more weight. While some other words may not be that informative and you want to give them low weight. Okay? So it's both, it depends both on the value of the feature and the weight that you give to it. Okay? And that is the connection between naive Bayes and logistic regression. Is that clear? So naive Bayes is a very restricted form of logistic regression where the features are fixed and the weighting of the features is fixed. You never learn, and that is why there is no learning phase in naive Bayes, right? So you just take the counts and that's it. There is no learning. Okay, but in logistic regression you have to learn the thetas. You have to optimize this function and find the optimal theta. Okay, that is the difference between the two algorithms. That's the connection and the difference between the two. So in general, you would expect that logistic regression would outperform naive Bayes given the right set of features. Okay, so and here, because there is a lot of flexibility that you have in designing features, it's both a curse and a boon. So if you really have domain knowledge, right, then you should be using that to design your features. Okay. Now one question that people frequently ask me is like, oh, how do I design features? How do I know that these are good features, or how should I design my features? Okay. So for that, think about this as an empirical rule of thumb. A practical tip is that think of every feature as a question about your data. Okay, so think of every feature as some question about your data, some discriminating question about your data. So here you could, for instance, suppose if you have text, you could ask, and you want to understand whether this email is spam or ham. Okay, so here you can simply say, okay, I'm just going to look at the words and ask for whether they're spam or ham. But here, for instance, you could design a feature which says what fraction of the data is capital letters versus what fraction of the data is lowercase letters. Or you could ask, how many times does a word begin with a proper capital letter versus how many times the word does not begin with a capital letter. Or you could ask, how many times does a punctuation mark occur in one data versus how many times it occurs in the other case. So these are all questions that you can ask, which have nothing to, here you are very restricted because you have to use the features or the words, whatever they are provided. Here you are, in some sense, you can design your own features. Of course, it's not saying that you cannot do exactly the same thing here. You can do pretty much similar things here, except that the sort of danger here is that every feature you introduce is weighed equally, which we all know may not be true. Like for instance, if you know that certain large fraction of words are capital, then that's a much more better indicator for spam than to say, okay, certain punctuation marks are occurring much more, but they should not be weighed equally. But when you go to naive Bayes, they get equal weight, but in a logistic regression, they'll get different weights. Okay, and you can also choose this theta flexibly by choosing a prior. So you might say, I know that I'm going to introduce 120,000 features, but most of the features I know are not going to be useful for prediction. Just like here you may say, I know that my vocabulary is very, very large. I have like 30,000 words in my vocabulary, but not all words are going to be discriminating. Then how do you eliminate these features? You add an L1 penalty here, and most of the values of theta will go to 0. If most of the values of theta go to 0, the corresponding features will be lost, will not play a role. Okay? So this is the connection between naive Bayes and logistic regression. Clear? Questions? Good. So now let us do one more thing with this, one more manipulation with this. Let us see how does this objective function look like for the case of logistic regression for binary classification. How does the objective function look like? And I'm going to take the gradient and try to understand basically what does the optimality conditions tell me, or what is it intuitively that this algorithm is trying to do. Okay, and then this will lead us into, when we talk about SVMs, I'll show you again, SVMs can also be derived entirely from arguments from the exponential family. Okay, so most people would tell you that SVMs have only a geometric interpretation, there is a margin, and then the margin is being maximized and so on. I will show you that you can actually use exactly the same kind of argument, and I can show you how the estimators produced by SVMs can also be viewed as being related to the exponential family. Okay, so they are very, very close, intimate relationship, and that is why in reality logistic regression and SVMs are much, much closer than people would like you to believe. Okay, so they are, and that's why it's not very surprising. If you see papers, they'll say, oh, logistic regression did 88% accuracy, SVM gave me 89, or the vice versa. They're very close to each other, right? And the reason for that is because they indeed are very close. They are very related, although people don't want to see it. Okay, so, but let's look at this. Let us look at the objective function. So in this case, the objective function for the binary classification becomes 1/2 norm theta square plus you have you know that p of y given xi theta looks like this. So this becomes summation I going from 1 to m of the log of 1 plus x of phi hat of x times theta. Okay, so this is how the objective function looks like, because you see this is the objective function, right? So this log p of theta is 1/2 norm theta square, and the log p of yi condition on x can be written this way. And if you take the gradient of this function and set it to 0, so let's take the gradient and set this gradient to 0. What happens to the gradient? So this is theta plus summation I going from 1 to m of 1/1 plus x of phi hat of x times theta times, I'm just applying chain rule, so this is x phi hat of x, there must be a y, I'm missing a y, yeah, that's right, okay. Times y times phi hat of x equals partial with respect to theta of j of theta. Okay, just plain chain rule. So log is 1/x, and then 1 plus x plus x, and then the gradient of y times phi hat times theta is y times phi hat. Okay, so just chain rule. Now look at this quantity. What can I rewrite it as? I can rewrite it as p of yi, of course everything is I, okay, condition on xi and theta minus 1 times yi phi hat of xi summation plus theta. Clear? So that's it. I think I might be making a sign error somewhere. No, this is fine. Yeah. Except I'm missing a yi here. Okay. So this is, you can verify for yourself that this is, no, I'm making a sign error, sorry. Doesn't matter. Okay. Modulo signs, okay, don't worry about signs in my lecture. You always have to go back and rederive all the equations for the signs. I'm more interested in giving you intuitions. So what is this saying? You want, because this is a convex function, right? You know that at optimality you want to set this gradient to 0, right? So when you find the optimal theta, this gradient will go to 0. Okay. For a minute, ignore this part. For just 1 minute, just ignore this part. Assume this is not there. Then what does it mean that the gradient goes to 0? This is a vector that's either +1 or -1. So this is going to be a vector. The only way that this gradient can go to 0 can be if this quantity, which is a multiplier, goes to 0. Right? This is like you are summing up some vectors. The sum of the vectors will go to 0 only when these coefficients go to 0. Okay. So if this coefficient goes to 0, what does that mean? It means this coefficient will go to 0 only if p of yi, condition on xi and theta, goes to 1. Right? So what does this mean? This is saying that in logistic regression, you are trying to take the true label and make its probability as high as possible. Ideally, you want it to be 1. Right? If you did not have this regularizer in a maximum likelihood setting, you are simply saying that if you give me data, I am going to find the parameter theta such that for all positive points, the p of y equals +1 is equal to 1, and for all negative points, the p of y equals -1 equals 1. Right? And this is what I am going to do, and I am going to try and find such a theta. Once I find that, that's my optimal solution. Okay. Now this is in some sense a very sort of democratic process. So let's see what. Let me try to show you what this means in a picture. Since yi is just +1 or -1, you can visualize this conditional distribution, right? So you can say what is p of y condition on x and theta, how does it look like? So at any x and given a theta, at any x you can ask, okay, what is the probability that y takes on value +1? What is the probability that y takes on value -1? Okay, so you can say, okay, the probability that y takes on value 1 is this, the probability that it takes on -1 is this, right? So you can, for any x and theta, you can ask this question, right? So and this will, you'll get a something like this. In some other case, the arrow may look like that and like that, but you know that these two, the length of these two arrows is going to add up to 1, and there are only 2 of them. Okay. And what this is telling you is that logistic regression says, I'm going to try and push the true class. If the true class happens to be -1, I'm going to push the true class up as much as I can so that it becomes this becomes 1, right? The height of this becomes 1, and here the height becomes 0. Okay, and then the vice versa for the other class. Now, intuitively, what this means is that in some sense, logistic regression simply says, I am going to take the true class and maximize its label. Okay, try maximize its probability. So I am going to make it as high as possible. Of course, implicitly in there is an argument which says that how can this be of height 1? This can be of height 1 only if this is of height 0. Okay, so implicitly in there is an argument which says that you should suppress the probabilities of the other classes. Okay, so when you are trying to enhance your own probability, you have to try and suppress the probability of the other classes, only then you will get more marks, because you know that the sum of the probabilities has to add to 1. Okay, so this is an implicit argument, this is an implicit sort of condition in there that you are trying to push the true label high and the other labels down. Okay. Now some of you may wonder, why do you do this implicitly? I don't need to do this in an implicit fashion and say, oh, I want to push myself up and push and therefore implicitly push the other guys down. Why don't I directly push the other guys down? So why don't I say, I want the true class to be significantly higher than everybody else, right? Which if that happens, then immediately I know that my true class will have a lot of probability mass. Right? See the argument? And I'll show you that SVMs are basically based on that second argument. So what is happening here implicitly is that you are trying to say, I don't care about the other classes, I am going to make my probability high, my true label probability very high. In an SVM you say, I don't only care about making my true probability high, I care about pushing everybody else down. Okay, it's like I can climb up only if others go down. Here this is like implicitly I can, if there is only a certain mass in the system, I can go up only if others go down. This is an implicit argument. An explicit argument is what SVMs mean. Okay, so that's the, so I'll talk about that. We'll derive for SVMs first in the very traditional geometric way, and then I'll show you how they're related to the exponential families. Okay. So any questions about this? So have you seen any of these kind of interpretations of logistic regression before? Good. Okay. Now finally, I just want to close this chapter by talking about what else can you do with this formulation, right? So we specialized it to +1, -1, and then we understood many things. But you don't have to necessarily specialize it to +1, -1. It turns out that even without the specialization, this is still quite powerful. And I'll just show you one example where sort of if you know this, how to derive this, you can basically derive a classifier for almost any kind of machine learning problem that you'll encounter, more or less. I mean, there are of course a few exceptions, but for any kind of supervised classification problem, you can derive classifiers. Okay. Oh, and one more thing I want to mention. I don't know if Prateek talked a lot about this, but there is one advantage to logistic regression, which is not there in SVMs. When we talk about them, we'll see that. Is that the objective function for SVMs is not only convex, but it's also smooth. Okay, so therefore you can apply certain class of optimizers which you cannot apply when you are using SVMs. Okay, and so you need a separate class of optimizers for dealing with SVM objectives. Okay. So let us take this objective function, and I'll very quickly just show you how to do multi-class classification with this. Okay, so suppose instead of just yi being +1, -1, let's say you just had the task of optical character recognition. So you have y is say 0 to 9. Okay, so you have 10 possible digits. You are trying to recognize digits, and now you have a problem where your labels could be between 0 to 9. And again, you are given some training data. Each of your yi's in the training data could be between 0 to 9. And now you want to design a classifier for this setting. How do you go around doing this? You do exactly the same thing as before. You crank exactly the same handle as before. The only difference being that now your g of theta, sorry, condition on x looks like log of sum of j going from 1, 0 to 9 of x of phi of x I j. Xj times theta. So now you have to sum over 10 possible values. And again, how do you design these features? Think of them as questions, right? So you can say, when the digit is 0, does something happen? When the digit is 1, does something happen? When the digit is 2, does something happen? You stack up these questions, those are your features. Okay, then the theta is the weight for the features. That's what the logistic regression is going to learn. It's going to learn how discriminative or how important is a certain question to discriminating between different classes. Okay, that's what the learning procedure is. This is how you compute the log partition function. Okay, so now given any problem, you can do this. But of course, as you can imagine, there is no free lunch. Why is there no free lunch? If you cannot design good questions, then there is nothing to discriminate, right? So let me just give you an example. Suppose you are trying to divide people into, say, whether they come from different parts of India. Now if you ask some relevant features, or if you ask some relevant questions about the features of the people, you are likely to be able to distinguish. But suppose if I just simply ask you, some random question about, oh, are you interested in photography, right? Maybe that is not a relevant question. It does, maybe everybody across all parts of India may or may not be interested in a certain hobby, or they may or may not be interested in a certain aspect, right? But if you just feed those features into your learning machine, into your learning algorithm, there is nothing to distinguish. There is no weights to add, there is nothing to distinguish. Okay, so it's basically garbage in, garbage out. If you provide features which you think can be discriminative, it's likely that you will learn a good classifier. So the right way to approach logistic regression, or in fact any of these other learning algorithms, is to say, I have to ask the right discriminative questions. What this algorithm is going to help me do is tell me the relative importance between all these questions. So if I feed it 100,000 questions, it's going to tell me that these 10 questions are very important, those 10 questions are reasonably important, the other 100 are much less important, and everything else is crap. Right? That's the mindset. If you approach your learning problem with this mindset, you'll get much more successful results. Okay? And this is a general purpose recipe. This is how I just showed you how you can immediately go to binary class, you can go to multi-class, you can do multi-label, ordinal regression, ranking, you name it, you can design using the same framework. The only challenge you have to really face is, in all cases, the only challenge is this. If your label space is small enough that you can compute this summation explicitly, you're home. There is nothing to do. But if your label space is very large, like for instance if you're doing ranking, okay, when I give you a list, so in ranking you're given a list of items and then you're given the ranking, right, so sort order. Now the problem in that case is that this set of all possible labels is the set of all possible ways in which you can rank this list, and that is exponentially large because factorial. Okay. And then the summation becomes painful, and this computing this guy becomes painful, and therefore your whole optimization becomes painful. Okay, so in that cases you have to do other more funny. You have to do other tricks to get around this. Okay, but if your label space is small enough that you can do this computation, this is all that you need to do. Okay, this is your general purpose recipe for computing, for coming up with any classifier. Okay, question?
When you design multi-class classifiers, is it better to have multi-class or train multiple classifiers as one against all? In general, what is it?
It's usually better to do multi-class. True multi-class is easy to do and should be done. It's just that again people did not understand the true, did not understand the connections between these different classifiers, and so they all started with one versus the rest and so on. In general, you would never be worse off doing a true multi-class than doing a one versus the rest. Okay, so that's usually the answer. That's the answer. Also, because there is something about interaction between classes which you are able to take into account when you do a true multi-class, which you are not able to take into account when you are doing binary one versus rest. Okay. How much time do we have? Okay, so we have 10 minutes. Let me. So, any other questions about this? Sijo, you have a question? No? So you understood everything. Now we'll ask you to come to the board. Let me switch gears a bit and talk about support vector machines. Today we'll try to do the more geometric argument, and then when we come back on Thursday I'll show you the probabilistic argument, the same kind of argument that we did for logistic regression. I'll show you how they are related, and again I want to show you the connections between SVMs and logistic regression when we come back. So let's do the geometric argument today. It's sort of simple, and I'll only do the hard margin today, and also we'll continue with the hard margin, and then we'll do the soft margin as we go along. Okay, so if I give you suppose I give you some data, okay, so let's say again similar setting. So you're given x1, y1, and so on up to x and y1. Okay, so you're given some data, labeled data, and again, for the sake of simplicity, +1, -1 labeled. Okay, so I'm just going to assume for this discussion that yi equals same simple setting. And now we want to find a classifier. Okay, so that's our goal. And we are interested in finding a linear classifier. Okay, so what it means is we are interested in finding a vector w and a number b. Okay, so, and I won't use the arrow all the time, but whenever I write w, it's a vector. So a vector w and a b such that this defines a hyperplane. So how does w and b define a hyperplane? W is the normal vector and b is the offset. Right? So it says how far away you are from the origin. So if you remember your geometry, this is the hyperplane is the surface that is perpendicular to w. Okay. So what that means is that you are looking at w times x plus b is equal to 0. That is this surface. That is the hyperplane. So w and b define this hyperplane. Now, if I give you any point, okay, in space, let's call this xi. Okay, so if I give you any point in space, and if you want to find out what is the distance of this point to the hyperplane, okay, you can do this very elementary geometric argument, and I encourage you to do this once at least, which is you can do this argument and you can immediately write the distance to be this. Okay, so you can say that the shortest, the perpendicular distance, so this is perpendicular, so the distance between xi and this hyperplane, okay, so the shortest geodesic that connects xi to the hyperplane has a length which is given by this. Okay, and there's a purely geometric argument. You can make this argument at least once. You should do it, and it's good to try. Okay, so this is nothing but the distance of xi. Okay, we are also going to call this the margin. Okay, so margin as in how far away is xi from this decision hyperplane. Okay, so we'll also use the term margin. Okay. Now, if you look at this argument, and if you look at how w and b are defining this hyperplane, okay, there is one slight catch. Okay, if you pay attention, you will see that catch. The catch is the following. If I take any non-zero alpha and multiply both w and b with that alpha, okay, this also defines exactly the same hyperplane. Remember, this is the equation, right? So if I just multiply this by alpha and alpha, nothing changes. Okay, so alpha times w and alpha times b also define the same hyperplane, it's the same surface. And this is a problem, right? So there's an identifiability issue. I could give you one w and b, and somebody else can give you the same w and b with a scaling factor alpha, and you will not be able to distinguish between them because they both define the same hyperplane. Okay, is that point clear? I see blank faces. So if I multiply w and b by a scaling factor, the surface that I get, if I look at this w x plus b or alpha w x plus b, if I look at the set of all x, right, such that this condition is satisfied, this is the hyperplane, right? If I multiply everything by alpha, this set is the same as this set. So therefore there's an identifiability issue. If you want to identify this plane by using w and b, you have a problem. Okay, so to get around this problem, what I'm going to do is I'm going to enforce the following condition. I'm just going to say w dot xi plus b the min over I going from 1 to m, I'm just going to arbitrarily set it to 1. Doesn't matter, I could set it to 42, nobody will care. Okay, but I just want to set it to some constant. In this case, I just choose the constant 1, but it doesn't have to be. Once I do this, you can immediately see that the scaling is fixed. Why? Because if I take w and b, if I multiply them by alpha, then this becomes this, right? And this is not, if this was equal to 1, then this is equal to alpha, mod alpha. Correct? So the scaling is immediately fixed. Do you see that? I cannot scale w and b by an arbitrary number, because if I scale them by an arbitrary number, this min would no longer be 1. The min would be alpha. Correct? So the scaling is fixed. So there has to be exactly one w and b for which this is satisfied. Any scaling of them, this will not be satisfied. This condition will not be satisfied. Okay? So once I fix this scaling in this way, then what happens? I can ask, if I give you a set of points x1 to xm that are given to me, I can ask what is the minimum margin. So what does it mean by the minimum margin? I am saying there are all these points lying here. Find me the closest point. Okay, so the closest point simply is, because we know this is the distance of the ith point, I am just going to do, this is margin for the entire data set. So I am going to say, for this set of points and this set of points, what is the closest point? And now because I have fixed this scaling to be equal to 1, my margin is simply going to be, because this quantity, the min, is fixed to be equal to 1, my margin is simply min over 1 over number. Right? So this is my so I don't need the min anymore, and this is going to be my margin. Okay? That clear? So just to recap, any hyperplane is defined by a normal and a offset, but there is a identifiability problem, which is you can scale your normal and offset by constant factor, and you will not be able to distinguish the hyperplanes because they are exactly the same. To fix this, what we are going to do is we are going to arbitrarily set this. We are going to say, if you give me some data, I am going to arbitrarily set that the min of w dot xi plus b equals 1 for this particular data. Okay, once you do this, the identifiability issue is fixed. And then you can ask, find for me the point which is the closest, or how far away is the closest point of this cloud, how far away is it from my hyperplane. That you can immediately write it as 1 over the norm of w, the 2 norm of w. Okay? And this is called the margin. So basically what you are asking is, how far away is the closest point? Oh shit, we are out of time. Okay, so how far away is the closest point from this cloud to the hyperplane? The answer is, it's 1 over norm of w. Okay, so next time we'll use this to derive a classifier, and then we'll talk about connections to exponential families. Okay. Questions? This is a geometric argument. You need to look it up and work it out once on your own. So please work this out once before you come. Then you'll be able to, you'll be able to enjoy the lecture better. So do this before you come. It won't be very hard. Okay. Thank you.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.